put your initials on every sheet. Try to staple it next time. And so our next quiz will be 2 weeks from Thursday. And I wasn't a big fan of the way the online thing went, so we'll just do it in class like a regular person. So that'll be on September 29th. Well, we have to see when we finish up chapter 2. Actually, you know what? That's not a good day. Let's postpone it one more class. So the quiz will be on October 3rd. Okay? And like I said, that'll be in person, regular old quiz. Yes?
What day was that again?
October 3rd, Monday, October 3rd.
Is that when the homework's due, chapter 2?
Well, we're going to have to see where we get by that point. What I might do is assign such that the quiz covers up to a question if we haven't gotten through all of chapter 2, although I think we will probably get through the whole thing by then. So, I don't know. That's the short answer. But what we'll do is by a week from today, by the 26th, we should be far enough to make a judgment call on that one. But as of right now, there's no due date for the chapter 2 homework. That doesn't mean that you shouldn't be starting it. My suggestion is to try to do the homework problems as we get up to that material in the book. And then that way you don't leave it all for the last day. And anyway, it's better to do it that way because everything's going to be fresher in your mind. Alright, so now the quiz. Just give me a second to make the canvas. Are there any other questions on stuff that people have?
It's not cumulative, right? Quizzes?
Well, I mean, here's the way I would answer that. The whole class is cumulative because what you see is that every subject built upon the last. It's not like history where kind of once you're done with the Revolutionary War, it's like the next topic. That being said, I normally don't ask a question that's focused on something from previous material. So like the chapter 3 quiz will not have a question that's very similar to a chapter 2 homework problem. It'll be more modeled after a chapter 3 homework problem, if you get what I'm saying. But it can still draw upon stuff from this book. Okay, so the quiz. Trying to look, see, sorry, I'm trying to see how I can see this the right view to show you. Question. Okay. All right, so the first question, passive sign convention dictates that P equals VI calculates the power injected in the system, not consumed from it. So that was false. Okay, right, we've said several times that the passive sign convention, how it relates to P equals VI, is, talks about power absorbed or consumed. Telegin's theorem provides the basis for derivation of, and the best answer for that one, I put Telegin's law. Oh, well, okay. Telegin's theorem is different. Look, if anybody put this as an answer, Telegin's law, which is not really the right answer, come talk to me. I didn't mean to make it a trick thing like that. But the answer was KVL, right? Because when we went through the book, we just explicitly discussed how KVL was derived from Telegreen's theorem. Law and Order SVU is a close second, so you will get half credit. No, I'm joking. All right, so imagine a resistor with 1.25 amps passing through it and a differential of 5.5 volts across it. What are the values of VR and IR after a short circuit is placed across the resistor's terminals? Note that this voltage and current satisfy the passive sign convention. So the thing that we know about a short, right, was that if we have a resistor and we place a short in parallel with it, first thing is that the current will take the path of least resistance, which means that none of the current will pass through the resistor, right? And we also know that a short by default has a voltage of 0 across it, so that would bring the terminal voltage down to 0. So the answer was the first one, okay, then the other ones were all different permutations, which were not the right one. Okay, what is susceptance? Right, it is the imaginary component of admittance. If you remember, right, impedance represents the relationship. So V equals I times Z, which is also equal to I times R plus JX. Okay, that's impedance. We also have and that's susceptance right there. If you remember, that was the one thing that I told you you had to memorize. But given the fact that this was an open notes, open book quiz, I can't imagine too many people got that one wrong. And so this is the one with the problem where the M didn't come across as a mu. So that one obviously will be fixed. And the answer would depend on whether you went off of 1 milliamp divided by 1 nanoamp or 1 micro, right? Because for this one, this would be 10 to the 3 difference because micro is 10 to the negative 6, and then nano is 10 to the negative 9, and this one would be a 10 to the 6 difference because milli is 10 to the negative 3, and then that's divided by 3. So, I mean, regardless of whether you know, the whole wording problem or the letter problem with this thing, just make sure you're up to date or you have a good understanding of what the SI units are. Again, that's something that's going to be on cheat sheets when we do the in-class quizzes, but I mean, it's just not something you want to be looking up every 2 seconds because you're going to use it so much that it's going to be a pain. Okay, so that was the quiz, and I will go through before Thursday and make all the necessary changes to the grades. Essentially what I'll just go through and do is everyone will get that question right. I'm not even going to bother trying to look at different permutations. Okay? So, picking up where we left off last time, so can someone tell me where we did leave off last time?
Thanks for example 2.17.
Okay. All right, so before we jump into new material, let's talk a little bit about some of the stuff that we did last time. Right, Chapter 2 has Chapter 2 has been introducing to us, right, the basics of electrical circuits with regard to KVL, KCL, etc. Last time, I think we touched upon a couple more advanced topics, well, advanced for the second chapter at least, which were voltage and current dividers, right? Those were two basic circuits that we can use One allows us to attenuate voltage, the other allows us to attenuate current or control the flow of current through a certain path. So those, first and foremost, should be circuits that you recognize pretty quickly, because you'll see them a lot, as you remember in the example, right? That was one that came up. So here, right, is a voltage divider where we essentially read the voltage across the output terminals. And then a current divider uses two resistors in parallel, and then we can pick one of the currents as the load current, essentially, that we're looking at, and then the ratio between those, this IL and the source, will be dependent on the ratio of these two resistors. So we have equations for that, and hopefully you understand how those work. We also talked about how to simplify circuits, right? Because if you remember, we said that before we get to chapter 3, where in chapter 3 we're going to start to talk about linear algebraic methods of analyzing circuits, nodal mesh analysis, which may not really mean anything to you right now, but it will in 2 weeks or so. In this chapter, what we're doing is we're really just using the basics to solve. And so the way that we do that is we take a complex circuit and we have to use parallel and series combinations to boil it down to one of the two different types. Okay, this is another way of saying a single loop, right? Remember we called the two circuits the single loop and the single node pair? For the single loop, right, the current through the entire circuit is the same, so that helps us solve. For the single node pair, the voltage across all the components is the same, so that helps us solve. You can also think of the single loop as being sort of like a voltage divider, and the single node pair sort of being like a current divider. So what we do is we collapse those circuits down to a basic type that we know how to solve already, and then we can expand it back out. And that was really the basis of what example 217 was all about, right? 217, we had this circuit here, okay, with a current source and then 3 resistors. And what we saw was we could combine these two in series, then we can combine these two in parallel, or we could recognize that that would be a current divider circuit. Then we could come up with individual values and divide back out. And if we wanted to come up with VO, we could say, all right, this is a voltage divider, and we would know what the ratio between VO and this voltage right here. So, right, it's sort of like an accordion, the way that we're going to address these problems. We're going to collapse them down from a complex circuit to a single node pair or a single loop. We're going to solve, okay, which in this case was for the voltage here. And then we expand it back out, depending on what values we want to come up with. And if we're not really concerned with VO, then we don't need to expand this back out. If we were only concerned with the voltage across that resistor, but most times we're going to be asking for multiple values. So today, what we're going to do is we're going to continue on with this material. Okay. So we haven't really... Keyboard stopped working, sorry. All right, so we haven't really discussed how to combine together all different types of sources. We touched upon it briefly. We know that voltage sources in series can be added together, right, because we did that whole loop example. But we didn't really talk about what would happen if we had voltage sources in parallel, or if we had current sources in series, and all the other different permutations there. So that's one topic that we have to discuss. All right, why is there nothing on the screen? No. There we go. So what I'm going to do is I'm going to draw a table, and that's going to cover the other cases that we haven't seen yet. So, So what happens when sources are combined in series and parallel? Right, we have 4 different cases that we have to look at. We have to look at the case of voltage sources. We have to look at the case of current sources. And then we have to look at both series and parallel. Now, with regard to independent versus dependent, it actually doesn't matter. Okay, so dependent sources are going to be added in the same way that independent sources are. The only difference is instead of adding 2 constants together, you're going to be adding together two functions, right, as a function of some other value of certain. Okay, when they're in series, 2 voltage sources, we kind of already know this one. So we have our V1, we have our V2, and I'm going to assume that they have the same polarity just for the sake of argument. Okay. So this I'm going to call V1, this I'm going to call V2, and so V equivalent equals V1 plus V2, with the polarity of the V equivalent being that. So for parallel combinations of voltages, this is inherently, well, let me ask you guys first. What do you think the rule is going to be for this? What happens when you put voltage sources in parallel? Well, I mean, it's a good guess. It's not the right answer. But think about it for a second, okay? Right? We know that voltages in a loop should add together even before we explicitly said it because KVL, right? We know that all the voltages in a loop should add to 0. So you could really derive this rule just from applying KVL to this loop. V1 plus V2 minus V equivalent, because it has the opposite polarity, equals 0. What about this? What happens if we apply KVL to this loop? What we end up with is V1 minus V2 equals 0. So KVL's got to be true. There's no ifs, ands, or buts about that. Which means that V1 must equal V2. All right? And this creates what we call a low impedance loop. What that means is, if you do this in reality, you're going to short out one of your 2 sources. Because if you think about it, the current flowing in this loop, it's going to be the difference between these 2 voltage sources divided by the series resistance, and the series resistance is 0, although when you're using hardware it's not really 0 because the wire has some resistance. So it would be a really small value, like let's say less than an ohm, and that's going to be a lot of current, everything's going to burn up. So there's 2 ways of looking at this. There's the theoretical and mathematical way or whatever, which is essentially saying that this doesn't work unless V1 equals V2. If you see in a problem or as part of one step in doing a problem, if you end up with something like this, 2 sources in parallel, you've done something wrong. Or there's a problem with the way that the problem is formulated to begin with, because this does not work. The other way of looking at it is with regard to hardware. If you're ever setting up a circuit where you put 2 voltage sources in parallel, 99 out of 100 times, I'm almost going to say 100 out of 100, you're doing something wrong. This is not what you want to be doing. All right. So current sources in series what about those? So a lot like how we applied KVL over here, we can apply KCL over here, right? So what would happen if I applied KCL to this node? Yeah.
I1 would equal I2.
Yeah. So this is a similar case to the one in the top left-hand corner. I1 must equal I2. And so this is one which you're much less likely to come up or to come upon in hardware, just because we don't really use current sources. It's funny because we talk about current sources a lot in this class, but I mean, transistors in certain cases can be current sources, but really they're not. Like if you look in our laboratories, like the ones we use for circuits lab, we don't have any current sources. So anyway, if you see something like this come up in one of your problems, or as a step in when you're doing work to solve one of them, you've made a mistake. And then lastly, what happens when we have two current sources in parallel? And so this is I1, this is I2, and that's I3. And so let's imagine there's a closed path there to flow. So there is some sort of a load. Because if I left it open altogether, then the current would be zero, right? So there's something over here that's allowing the loop to be closed or the circuit to be closed. What would I3 be? And if we apply KCL at this right here, we should see that the answer would be I3 is equal to I1 plus I2. All right, so you can see that there's really only two cases that we're going to be particularly concerned with. And that is case 1 over here, case 2 over here. Those are the ones that you're going to have to look out for in the problem. Okay, so I think we've already talked a decent amount, so we have already discussed how to simplify series connected circuits. What about parallel? And this shouldn't be any mystery because we've already given all the different pieces to this puzzle. We know how to connect, or we know how to find the equivalent of resistors in parallel, right? The simplest one, if we're just talking about two resistors, is the equivalent equals R1 times R2 over R1 plus R2. And we know that current sources combine in parallel. If you have the case where you have voltage sources in parallel, then something is wrong. So let's take a look at an example like this. Try to copy what I did last time. Okay, so what we have is, I'm going to call this V out right here, plus minus. This is I1, this is I3, this is I4, and this is I6. This is, we're going to call it R2 and R5. And then the currents are just going to have the same
the same name. So this current here would be I2, and this current here going through R5 would be I5. And the only reason why I'm going to add that minus right there is because I want to satisfy the passive sign convention, so you can imagine the arrows are pointing in another direction. I hope that's not confusing, but I can't really erase the arrowheads, so I'm kind of stuck where I am. Now, so how do we simplify something like this? It's very similar to what we did for the loop. The first thing you have to realize is that for a single node pair like this, and actually that's, I guess I shouldn't use the word single node pair because that implies that there's only two elements. So this, I guess, would be a single node group. Well, no, it's talking about a pair of nodes, so that's actually still the right term. Sorry. Anyway, for a single node pair like this, order doesn't matter. Remember, we said the same thing about the single loop. So we can move things right and left however we want to, which means we can redraw this circuit like this. That has no effect on the solution for V out. And then what we'll say is that this is I1, this is negative I3. I switched the direction. This is I4, and this is negative I6. And so to group these together, right, this would be a single current source. Right, we could say that's a single current source with a value of I equivalent equals what? I1 minus I3 plus I4 minus I6. So I1 minus I3 plus I4 minus I6. And then those two would be an equivalent resistance, which would be R2 times R5 over R2 plus R5. Hopefully that makes sense to everybody, given what we went through in the past class or two. Okay, so how would we rewrite this? We can simply have it as a, I'm going to try to draw things a little bit bigger because I realize it's done a little small. We can simply have this as a single current source and a single resistor, and this resistor would be your R equivalent, and this would be your I equivalent, right? And your V out will stay the same. So now we know how to simplify or to solve for single loop type circuits as well as single node pairs. And maybe it goes without saying, right? Right, obviously VO will be equal to I equivalent times R equivalent. So that's sort of the end result we were trying to get to. All right, sorry for my Okay, so let's do another example. So this is example 2.19. And yeah, I'm going to try to draw a little bigger from now on, right a little. All right, so we're going to solve for all unknown values. So it's resistor current, resistor current. And then lastly, we have our load resistance. All right, so this is 18 kiloohms. This is 9 kiloohms. This is 12 kiloohms. This is 12 kiloohms. So we have 1 milli, 4 milliamps, 1 milliamps, and 2 amps. And lastly, so there's two values that we're looking for. So there's two values that we're looking for. We're going to be looking for the voltage VL, which is going to be right here. And we're also going to be looking for the current IF. Okay, which looks like that. Okay, so first step, as always, is going to be to label everything. Now, we're going to slowly migrate away from this as we get further and further on into the book. Because as the circuits get bigger and you get better at these types of problems, you don't necessarily, you can kind of define, you can label things on the fly as you need them. But for now, we'll keep doing it. So there's no need to label any of the other voltages across any of these components, right? Because this is, hopefully, you all picked out as a single node pair. Again, single pair of nodes. Node number 1, node number 2, all right? And the only thing left is to define the currents. And so what I'll do is I'll define them all using the passive sign convention. And we don't have to do it for the resistor. So we'll call this IR1, IR2, and IR3. Okay, so that gives us everything that we need. So we labeled everything. Step number 2. All right, we're gonna simplify, right? Because that's pretty much the only way that we know how to solve these types of circuits. So there's two different choices that you have here. So the first choice is you could combine everything down All right, you could combine everything down to a single source and a single resistor and solve for VL. So what that circuit would look like is, would look something like this. Where this would be an I equivalent, and this would be an R equivalent, and this would be your VL. Can anybody think of a better way to solve this? If we're trying to find IL, right, then you'll see that in this circuit down here, we've lost resolution when it comes to calculating IL, right? IL no longer exists in the simplified circuit. So a better way, or another way to do it, might be to combine everything but the 12 kilo ohm resistor, such that we have a current divider. Okay, so that would give you something that looks like this. And the reason why I put a prime right there is because this R equivalent is different from this R equivalent, right? Depending on which way you did it, it would give you different answers. And now you would still have your IL. So, I mean, it's really not a huge difference, okay? I mean, there's only one more step you would have to do in this one, and that would be to calculate IL would be to take the VL and divide by 12,000. So, right, the next step would be to say IL is equal to VL divided by 12 kilo ohms. It's not like it would be another hour's worth of work, but I'd like for you to start being able to think ahead in that way, where you don't necessarily solve everything down. Think about what it is, what base circuit, which in this, given what we know right now, is really going to be single node pair, single loop, voltage divider, current divider, even though a voltage divider is what form of circuit requires you to do the least amount of simplification, but still allows you to solve? Okay? So why don't we go this route right here? And so what we'll do is, hopefully we can kind of eyeball this. I'm hoping that we've gotten familiar enough with this stuff where we don't have to necessarily write out every single step. And actually, we're not on a different step. We're still on step number 2. All right, so what would I equivalent be? It would be, so if I'm trying to bridge everything here. So if we have this I equivalent with this reference direction shown, what's going to be I equivalent? Exactly. So that's negative 1 million. All right. So good. What's R equivalent prime going to be, given my definition of R equivalent prime here? So we got to combine 3 resistors. We got to combine this, this, and this. And the form that we saw for that was, we can say that 1 over R equivalent prime is equal to 1 over 18K plus 1 over 9K plus 1 over 12K. If you remember, right, the the admittances sum in parallel. And so, what's the answer? 4,000. Okay, so I'm assuming 1 over, this equation would actually be 1 over 4,000, right? And the R equivalent. Yeah, I'm not correcting you, I just want to make sure I write it down on the sheet of paper. Okay, so just to be completely, to agree with my equation, it should be 1 over 4,000, which gives us an R equivalent of 4,000. Okay, good. And then, right, we know what the last value is, that's going to be 12,000. So if I redraw the circuit, okay, we have negative 1 milliamp, we have our 4 kilo ohm, and we have our 12 kilo ohm, and we have our IL. And now what we can do is use the current divider to solve for IL. So that would mean that IL is equal to negative 1 milliamp times, and what's that going to be right there? So if you remember right, the equation for the current divider was a lot like the equation for the voltage divider. Right, except in the numerator you have the quote-unquote opposite resistor, right? So instead of it being 12K over these two sums, it's 4K. So you have 4,000 over 4,000 plus 12,000 ohms. Right, this is just your current divider equation. Well, I already wrote that up, but whatever. I'm already writing it again. So what is that going to give us? So this is 1/4, right? So negative 0.25 milliamps. And then VL okay, someone, well, I guess that would be 3 volts, is that right? Because the milli and the kilo would cancel out, and then we'll negative 3 volts. The milli and the kilo would cancel out, and 1/4 of 12 is 3. So if you go back and look at this sheet right here, you know, really, I guess a better way to talk about these two options is, this is easier to calculate VL first, and this is easier to calculate IL first. So it's really not a matter of one being better than the other, but which value you're more concerned with. Perhaps it's a little bit too early to be drawing very, very specific distinctions like this, but anyway, something to. There's more than one way to solve these types of problems that we're doing.
Any questions on that one? I don't think there's any. Okay. So now what we're going to do is we're going to dive into some problems where perhaps things aren't drawn the way that we expect them to be drawn. And what I mean by that is, you'll see in a second when I draw the picture. We're used to seeing the circuits drawn in a certain way with nice 90-degree angles and everything's vertical and horizontal, but things don't necessarily have to be drawn like that. And one really interesting thing is I've seen students have problems picking out parallel and series and those types of connections just because things are drawn differently. And so take a look at this picture right here, or at this circuit schematic right here. So we have some diagonally drawn resistors. And you'd be surprised how often stuff like this has thrown students for a loop in the past. Okay, and so we have 2, 4, 2K, 4K, 2K, 6K, 9K, 6, 1K, 2K. All right. So So to begin simplifying this thing, we need to identify what resistors are in series / in parallel. And just to make this a little bit easier, well, I don't want to use letters because they already call it RDE. So do we have any series or parallel combos? And here you can see what I mean by the fact that having stuff in parallel just sometimes, until you get used to seeing it like that, can make it a little bit. So remember, what are our rules for series and parallel? Okay, the rule for parallel is that the two impedances, or resistances, whatever we use, must share the same end nodes. Okay, there's actually no other specification, there's no other requirement other than that. For series, they must share a single node, and there can't be anything else adjacent to that node. So let's take a look at some of these different combos. These two, are they in series? Nope, right, because we have a whole bunch of stuff out of here. They're obviously not in parallel. And I'm not going to go through every pair, but is this in parallel with these two right here? Actually, it is. But we don't want to make that combination because that would get rid of node B, right? So that really wouldn't help us too much because we want to keep B in there. So, right, because if we did that simplification, we would be finding the parallel impedance between A and whatever we call this node. Are these two in series? No, I mean, right? Okay, so anyway, to make a long story short, these two, they are
They are in series. So that's our first discovery. And then the other thing we can see is that that this 6 kilo ohm resistor is in parallel with both of those, right? These two resistors, if we think about them as a single one, because we're going to combine them in a second, they share the same end nodes with the 6K. So if we want to start trying to do multiple steps at once, and because if you don't, right, this is going to take a long time to simplify this. What we could do is combine all three of these together. So, and what I'll do is, which will help us here with the discussion, is I'll name the rest of these nodes. So this doesn't need to be named. This will be node D. This will be node E. That will be node F. And this will be node G. So we're going to combine the 6, 1, and 2K resistors across nodes E and G to calculate R, E, G. Okay? And so what we'll do is we'll redraw the circuit. Unfortunately, problems like this in the beginning when we're redrawing a lot are going to take me a little bit of time to write everything up. I'll try to do it as quickly as I can. And I'm relying on you guys as I redraw things a lot to help me out if I make a mistake. And what I mean by make a mistake is if I copy something down wrong. Okay, so we have 2K, 4K, 3K, 6K, 10K. All right. And so these are still nodes C, D, E, and G. And node F is gone, right? And we expect node F to disappear because it's in the middle of that series combo that we just made. So what is this REG going to be equal to? I'll write it down here and I'll copy it up top. So REG is equal to So what is REG going to be equal to? Hopefully you can eyeball what the series combo of 1 and 2 are, right? That's going to be 3,000. So it's going to be a parallel combination of a 6 kilo ohm resistor and a 3 kilo ohm resistor, right? So it's going to be a 6 kilo ohm resistor in parallel with, and I'll write out the full thing, 1 kilo ohm plus 2 kilo ohms. Where this represents the parallel combo, this represents the series. And so what we end up with is 6,000 times 3,000 over 6,000 plus 9,000. So that's going to give us so 18 million over 15,000. Anyway, can someone do that on a calculator? No, I'm not going
Would it be 6,000 plus 3,000?
to. Oh, yes, I'm sorry. You're right. You should probably look at the math out easier. Yeah, 18,000 over 9,000. Is that right? 18,000 over 9,000. Or 18,000 over 9,000, 2,000. That's what you got in the calculators? Yep, all right. So 2,000 ohms. All right, now, what combo can we make? Right, you can see that we'll have the REG and the 10K in series, and those both will be in parallel with the 6K. So it's kind of a similar situation that we had before, where now these will be in series, and they'll be in parallel with, I know there's a lot of arrows going on here, but these will be in parallel with this guy. This is a tedious example, I know. Okay, so the resistance now we're going to have is going to be RDG. Okay, so right. So we have 2 kilo ohms, we have 4 kilo ohms, we have, I'll remember the diagonal.
Is there still that 9?
Yeah, thank you, I was just looking at that. 2 kilo ohms, and now we have RDG. So this is still C, this is still D, this is still G. Pictures are getting sloppier and sloppier as we move on. Okay, so RDG. What's going to be that? It's going to be a 6 kilo ohm resistor in parallel with what? 12,000, exactly. So that'll leave us with, 6 kilo ohms. Sorry, I gotta move up. 6 kilo ohms in parallel with 10 kilo ohms plus 2 kilo ohms. Okay. So can someone just calculate that for me? Right, it's going to be 6,000 times 12,000 over 18,000. Can some other person just do that? I just like to get 2 people. That way we don't go down the wrong path. So I'm just selecting anybody else. Yeah, anybody else get that? Okay, you got some nodding hands. All right, so that's 4,000. So that is up there. Anyway, hopefully you can see where this problem is going. So what I'm going to do is, I can't draw anymore. My hands are tired. So I'm going to say you're gonna finish this on your own. Actually, if you look in the board notes that are posted on the website, it goes through every step in detail. But I feel like we're getting repetitive here. Yes.
I'm just curious, would you recommend like drawing the circuit? I learned it in physics to draw it in like a vertical alignment so you can easily see what's in series and what's in parallel.
Yeah, I mean, I think that's, I know the way you're talking about, that's a perfectly good way to do it. It's probably not the way we normally do in electrical engineering, but really whatever works, you know. Because I think that, you know, as you get more and more used to the material, you're going to draw fewer and fewer pictures. Like if I were going to do this, I'd probably just kind of imagine the picture in my head and bring it down. So, short answer, yeah, that's I think a good way of doing it. Whatever you feel most comfortable with. Okay, so anyway, I'm going to say but in the end,
what you should end up with, and I'll switch over to the board for 1 second, is, so let's see where we left off. We got to 2K, we got to 4K, and then anyway, you do the rest of them, and you end up with a 5K at the end. Everybody, I think the first 2 steps kind of gave a good explanation of what was going on there, right? There's no... Okay, so now, section 2.6 is going to be circuits with both. And, you know, I really feel like we've done a lot of these examples. So I'm going to talk through this one on you know, on the screen here, and I'm not going to write every step down. But I think we'll get another view. Okay, so, but I will go through it pretty quickly. So this is example 224, which is from section 2.6, and this is for circuits with both parallel and series. So this example asks you to find VC, which is the voltage right here. And as you can see, what we're going to do, combine these two together, boom. These will be these two will be in series and parallel with that. Then you have these two series and parallel with that. And then what you'll end up with is a single loop at the end, where the resistor right here will actually be these two in series and parallel, these two in series, and you get it. Okay. Once you get this single loop, right, this will be a voltage divider. So what you'll do is you'll define the voltage here, which is going to be different than VA, right? VA is with the resolution of seeing the entire circuit. The value that you're actually going to get right here is going to be a different equivalent value. So once you have a single loop, you can treat this as a voltage divider. You can solve for the voltage across these two terminals and then expand it back out. So let's take a look at each one of the steps. Okay, so this is the first step in collapsing the circuit, which is to combine the 9,000 and the 3,000 ohm resistor in series and the 4K ohm. And so you can see what we've done is we've used the method with the 1 over the admittance. Okay, so we have 1 over 4,000 plus 1 over series combo. So the equivalent resistance right here is 3,000. We're going to do the same thing again, which is going to give us an equivalent resistance of 3,000. Actually, I was wrong. I'm sorry. This is still going to be VA, right? Because of the way these combine, these two nodes are not going to be lost with resolution. So you can still call this VA. All right. So is this simple enough? Yes, it's simple enough. It's a voltage divider, and so we can calculate VA as 3,000 over 12,000 times 12 volts. All right, so that'll be 1/4. So the voltage VA will be 3 volts. Okay, and then what you can do is actually work your way back out without drawing any more circuits. Because if we know this is 3 volts, okay, this is VA, it's the same as this VA, then what's VB going to be? It's going to be 3 volts times 3,000 over 3,000, right? You have a second voltage divider. So that will give you 1/2 times the 3, which will be 1.5 volts. And then going back to this one, we'll have 1.5 volts times, this will be 3,000 over 9 or over 12,000 times 1.5, and that'll again be 1/4. And so whatever 1.5 divided by 4 is, which is less than 1. So you can see the numerical answers here. Okay, so you have VA is 3 volts, VB is 1.5 volts, and VC is 1/4 of 1.5. So, right, the process, again, was essentially boiling it, making the series in parallel combinations to break it down to a single loop, solving for that voltage VA, and then breaking it back out using the voltage dividers. But the good news is you don't have to draw as many circuits. Does that make sense, everybody? Yes.
So, in this equation, you're using the equation for voltage dividers over and over again.
Sorry, say it again?
The equation you're using to find the new voltages.
Yeah, so it's, if you can see here, I maybe didn't explicitly write it out in the second one, but you can see, right, so the first equation is starting from the simplest circuit, right, so that's, 3 over 12, 3 over 3 plus 9, and then 3 over 3 plus 3, and then 3 over 3 plus 9 again. So yeah, those are voltage dividers. Okay. So take a look at those two examples. I mean, we went through most of 220, but 224. Okay, so now we're going to get to a whole new topic, which is section 2.7. And this will actually be good because we have about 10 minutes left, and I've got thinking about 10 minutes to introduce this topic, and then we can keep starting on some examples. So section 2.7 it's called the delta to Y transformation. So what we're going to see here is that there are certain combinations of resistors which we can find an equivalent for, but are not either series or parallel. Okay, and so the two different combinations that we're going to deal with, they are, each one is going to be a 3-terminal combo. Okay, where you can think about series and parallel being 2 terminals, right? Because they have 2 terminals. This one's going to have 3. So we'll call the terminals A, B, and C. And this I'll call RA, this I'll call RB, and this I'll call RC. So this is the Y form, okay, or the Y configuration of 3 different resistors. The other version of this, or other configuration form, whatever word you want to use, this again will be A, B, and C. So this, hopefully you recognize, right, what is the So the reason, right, these two circuits or these two configurations have their names is because they look like the letters, right? The Y looks like the letter Y, and the delta looks like a letter, the Greek letter delta, or at least the capital. And so the transformation allows us to go back and forth. And so what we'll see is that this is useful in a lot of circuits. Well, not a lot, but I mean, some. I don't know what is there, but because sometimes when we're trying to apply the method that we were in the last 2 examples, where we're simplifying things down, you'll find cases where You don't have any circuits in series, and you don't have any resistors in series, and you don't have any resistors in parallel. Which, if you didn't have knowledge of this, you'd be sort of just at, there's nothing you can do with it. So another tool that you have in your possession, in addition to series combos and parallel combos, is going to be this delta to Y or Y to delta transformation. And so, after using this transformation, you can potentially put some resistors in parallel or series. So I guess what I'm saying is the resistors might initially be in this form. There's nothing in parallel or in series. Then you change to this form, and now you have some parallel and series combos you can use to solve. Or the opposite. The resistors are initially in this form, and you switch to the other one. Okay. The good thing about these combos is that there can be other resistors adjacent. So it's not like the series combo, right, where that middle node has to be unconnected to anything else. So these are the nodes A, B, and C, they can't have other parts of the circuitry on. That's completely fine. You can almost imagine when you do this transformation as like you're cutting out that part of the circuit with like scissors, pulling it out, and putting something right back in its place. So the most important thing is that you keep track of what's A, what's B, and what's C. The most common mistake would be accidentally rotating. Okay, and then obviously that's not good. Okay, so what's an example of when this would be useful? So let's imagine we have a circuit that looks like this. Okay. So, taking a look at this, can anything be combined in series or parallel? So I'll give these names. So I'm going to give these nodes letters just to help us with the discussion. A, B, C, and D. And so this will be RAB. This will be RBB, this will be RCD, this will be RCA, and this will be RBC. So can anything be combined in series or parallel? No. So you're stuck, right? At least given what we know right now. Okay? But what if sorry, my spelling is getting very dicey there. But what if we apply a delta to Y transformation? And I just happen, well, not happen to,
but intentionally, name these nodes in the right way. So we have R, A, B, C, and you can tell that this right here is a delta configuration of the resistors, right? So let's apply a delta to Y transformation, which we don't know the equation of it yet, but we know it's possible. We'll discuss the equation in a second. So what would the new circuit look like? Yeah, I'm going to have to try to jam this in here. Okay. What we would have is, okay, the most important thing, right, is we have to replace RB, all three of the nodes. It's like we're cutting this chunk out and replacing it with a Y. So that means that what we're going to end up with is something that looks like this. And I'm sorry I have to draw it small, or else it won't fit on this sheet. So this is still node A. This is still right here node B. This is still node C. And this is still node D. If you remember, right, we don't lose any resolution with regard to the nodes when we do the delta to Y or Y to delta transformation. We're going to rename this RA. We're going to rename this RB. We're going to rename this RC. These other two resistors stay the same. They're still RBD as they were before, and RCD. Anyway, the picture's not very good. I didn't have much space. But can we make some combinations here? So, what's the answer? Yes, we can. Right, RB is in series with RBD. RC is in series with RCD. And both of those are in parallel with each other. And then those parallel combinations are in series with RA, right? Anyway, you have to kind of look at it and figure out, see what's going on here. But anyway, to make a long story short, yes. So, next time we'll have to get to the actual equation. But I think this is almost the more important piece of it, which is illustrating why we care about doing this. Okay, the Y to delta and delta to Y transformation is something that allows us to reformulate a circuit and hopefully give us a path to solving when we didn't originally. All right, so I'll see you guys on Thursday. And if you don't have your quiz grade cleared up by Thursday, if you